Hi, I'm Jinhyuk from Fusion-in-University, and I'm going to present our paper called Phrase-retrieval learns passage retrieval 2. This is a joint work with Alex Wettig and Danqi Chen. In open domain question answering, a model is given an open domain question and tries to find an answer from a large corpus like Wikipedia. Many open domain QA models use a pipeline approach where a document retriever is used to retrieve relevant documents, and a document reader like BERT is used to find a short answer for this question. This type of retrieval-reader approach is becoming more popular these days, and reading hundreds of passages for each question using a heavy reader model makes the entire process very slow. Our work builds on a paradigm called phrase retrieval for open domain question answering. Here, phrases are any contiguous segment of text up to L words, and in phrase retrieval, one of the 60 billion phrases in Wikipedia is retrieved based on the maximum inner product search with the question vector. DensePhrases is a phrase retrieval model that uses dense representation of phrases and questions. In terms of end-to-end open domain QA accuracy, DensePhrases is competitive with retrieval-reader approaches even without using any reader model. And it also makes open domain QA much faster and simpler, and end-to-end open domain QA can be efficiently implemented purely with CPUs. We motivate our research from the observation that many retrieval methods have fixed granularity of text to retrieve. For instance, we had to encode a sentence for sentence retrieval, or encode a passage for passage retrieval, while the definition of passage often changes in different models. Does this mean that we need a different index for different granularity? In this work, we use phrases as a basic retrieval unit for building a single index for multi-granularity retrieval. For instance, given a question like, "Why is the sky blue?" phrase retrieval might return the following phrase as an answer. But for a question like this, we might want to retrieve a full sentence that describes the reason behind it. Luckily, in phrase retrieval, once we locate the phrase, we can actually retrieve its sentence, passage, or even the document that contains this phrase. This means that retrieving phrases entails retrieving any larger granularity retrieval units, while the opposite direction doesn't really hold. And this enables us to have a single index for multi-granularity retrieval. In this paper, we try to answer the following research questions. First, if we use phrase retrieval to retrieve passages, does it work better than passage retrievers on passage retrieval tasks? Second, if it works well, then why does it work? What's different from passage retrievers? Lastly, since the number of phrases is much larger than the number of passages, how efficiently can we implement this? We first give a formal definition of our method. In passage retrieval, a model creates a single vector for each passage. We use DPR as the standard passage retriever. On the other hand, in phrase-based passage retrieval that uses phrases to retrieve passages, a model creates multiple phrase vectors for each passage, and the passage score can be defined as a maximum phrase score within the passage. Here, the large SP denotes the set of phrases in the passage P, and we can flexibly change the retrieval unit by taking max over a different granularity, like a sentence. Here, we use DensePhrases as a phrase retriever. In our first experiment, we compared DPR and our phrase-based passage retrieval on the passage retrieval task for open domain QA while using phrase retriever as an off-the-shelf tool without any retraining. Here we showed the top K retrieval accuracy of DPR, meaning whether the answer is in the top K retrieved passages or not. Note that we made the comparison as fair as possible, making DensePhrases retrieve exactly the same granularity with DPR, which is a 100-word passage. Surprisingly, without any passage-level training signal, DensePhrases easily outperform DPR on this task, while the gain is larger when the K is small. We further test this phrase-based passage retrieval for end-to-end open domain QA using state-of-the-art retrieval-reader approach called Fusion-in-Decoder. Fusion-in-Decoder feeds top K passages from DPR to a generative model called T5 to generate answers, but it requires a large number of passages to accurately generate an answer. This often requires a number of large memory GPUs, which is often difficult to afford in academia. Here we replace DPR to DensePhrases and train FID to see if there is any improvement. Note that without such pipeline approach, DensePhrases alone can retrieve phrase-level answers as well. In our second experiment, we measured the open domain QA accuracy comparing FID-based DPR and FID based on DensePhrases. FID with DensePhrases largely outperforms FID with DPR, especially when the number of given passage is small. We can also see that feeding only 25 to 50 passages is enough to reach the max performance of existing FID and is more resource efficient. So why is DensePhrases better than DPR on this past retrieval task? In our paper, we compared these two models by looking at their objective functions. Given the question vector for each model, they first represent the positive units as follows: DPR using CLS and DensePhrases using phrases. For negative units, both of these models use in-batch negatives that are locally different, that are topically different from the positive ones. Notably, DPR has BM25 hard negatives that look similar to the positive passages but do not contain the answer. On the other hand, DensePhrases has in-passage negatives that are not only similar but exactly the same passages as the positive ones, and the model is required to differentiate two different phrases in the same passage. In our paper, we show that these in-passage negatives in DensePhrases actually work very similar to the BM25 hard negatives in DPR. We further characterize each model using the following two losses, L-topic and L-hard. Given a positive passage that contains an answer, x plus, L-topic measures how well a model can retrieve the positive passage when given a topically different passage, x minus. On the other hand, L-hard measures how well a model can retrieve the positive passage when given a topically same but answer missing passage. For both metrics, lower numbers are better. And in our paper, we find that DPR has good L-topic, while DensePhrases has good L-hard thanks to its in-passage negatives. So what does it mean to have good L-topic or good L-hard? Here we give a more intuitive example of how DPR and DensePhrases work. Given a question like where is Princeton University located, we find that both DPR and DensePhrases give a correct answer, Princeton, New Jersey. However, while DPR found the answer from a topically relevant document, which means that it has good L-topic, DensePhrases retrieved the correct answer from a topically less relevant document, New York metropolitan area, which means that it can search fine-grained information in each passage regardless of their topics. So good L-hard means that DensePhrases can give correct answer even when the passage is less relevant. Although having good L-hard is sufficient for open domain QA, many coarse granularity retrieval tasks, such as document retrieval, only requires topical relevance. For instance, entity linking would require the retriever to retrieve a single topically relevant document, and knowledge-grounded dialogue also requires a single topically relevant document. So we tested DPR and DensePhrases on the entity linking and dialogue tasks in killed dataset, where only one document is annotated to be topically relevant for each query. So our third experiment tests our model on the document retrieval task for entity linking and dialogue, and here is the baseline performance of TF-IDF and DPR. On these two tasks, DensePhrases perform very poorly compared to DPR and TF-IDF since it is less sensitive to topics. In our paper, we propose to fix this problem by fine-tuning DensePhrases to maximize the probability of any phrases contained in the relevant documents. This means that we maximize the marginal probability of any phrases in the relevant documents. By using this approach, DensePhrases can easily outperform existing models, and this means that DensePhrases can be easily adapted to coarse granularity retrieval tasks where topical relevance matters as well. Finally, we tackled the efficiency problem of our model since we need multiple vectors per passage, similar to the previous work on multi-vector encoding models. Compared to DPR that stores 21 million passage vectors, DensePhrases has to store about 500 million phrase vectors, and this makes phrase indexes much heavier, like 1.2 terabyte, 1.5 terabyte, and 320 gigabytes. In our paper, we show that we can do more aggressive phrase filtering with a learned phrase filter. And we also apply product quantization with quantization-aware training to safely reduce the size of a phrase index. Combining these two techniques, the index size of DensePhrases, here the blue dot, can be greatly reduced with minimal performance loss compared to DPR, denoted as a brown dot. First, applying product quantization largely reduces the size of the phrase index, and the phrase filtering gives us a good trade-off between the accuracy and the index size. We can even reduce the size down to 23 GB, which is much smaller than DPR, and having 8.8 vectors per passage in DensePhrases has similar accuracy with DPR while having only a 30 GB index. To conclude, we showed that DensePhrases is actually better than DPR on the passage retrieval task, while it can be used to achieve strong optimal QA accuracy very efficiently. Also, we find out that DensePhrases is better because it captures fine-grained entailment of answers, while it can be adapted to coarse-granularity retrieval as well. Lastly, we showed how efficiently we can implement phrase retrieval by safely reducing the index size down to 23 GB. All of our code and pre-trained models are publicly available, and thank you for your listening.